Hey there, geometry. Missing you guys. I hope you're having a good week and getting into some good rhythms. We are going to jump into 8.2 tomorrow. You have an assessment and it's only going to cover 8.1. So if you do not understand tangents yet, don't worry about it. We're really not even going to go into too much depth. I just wanted to get us a little bit introduced to the topic. Take a couple notes in your notebook, and then after Easter we're going to jump more into really using them and using some of the information from 8.1 as well. I think circles are really important. We don't want to fly through it, but we do have to kind of keep moving along at the same point. So rewatch this stuff if you need to. Your quiz again or assessment tomorrow is only going to be 8.1. So we're going to maybe do 1 or 2 practice problems that'll cover that, but this is mostly going to be 8.2. All right, let's jump in. Okay, so 8.2 tangents, label this in your interactive notebook. Let's start with a little bit of review. So we have a circle. And we've got this center point, and a circle is named after its center. So if this was a C, then this would be called circle C, and that's how we would write it. Just like we might write triangle A, or we might write rectangle B, well, we will call this circle C, okay? So let's talk a little bit about some of these points on here, or lines as well. So our red line is what? Take a second, think about that. If you said radius, you're right. The red line is a radius. A radius starts in the center of the circle and it goes out as a straight line to a point on the circle itself from its center point. What about this green, dark green line that we have right here? Do you remember? It's twice a radius. Yes, if you said diameter, you're right. There's our diameter, and it goes from one point, or one of its endpoints is on the circle, and it goes through the center right here. I should get my pointer. Through the center right here, and its other endpoint is also on the circle. Okay, but uniquely, it goes through the center. Okay, now I say uniquely because we also have this line right here, and it has an end point on the circle and an end point on the circle. So why is that not a diameter, you might ask? Well, this is called a chord. Sorry, I should have asked you, didn't give you a second. So this yellow one over here is also a chord. So any diameter is technically also a chord. It's a unique type of chord because it goes through the center. But a chord, by definition, is just some line segment whose endpoints are both on the circle, okay? All right, now we also talked briefly before about a line who has 2 intersections in a circle. If it goes through the circle 2 times, at those points just drawn, and it is a line segment, which means it will go on forever and always both ways. What is this called? Do you remember? This was a new word. If you said secant, you were right. Okay. Now, today's new vocabulary word that we're going to talk about is a tangent. And it is also a line, so it's similar to a secant in that it's a line. Here's my pointer. Okay. It's going to go on and on. It's not a line segment with endpoints. It's just going to go on and on. But instead of intersecting this circle at 1, 2 points like a secant, it's only going to intersect uniquely at one given point, which means it kind of just touches, it grazes the edge of the circle. And those are really the only other choices. It's either going to go through a circle twice, or it's just going to touch at one point and keep going, because otherwise it won't touch at all, and there's no way for it to touch 3 times, at least in Euclidean geometry. Okay, so here is my tangent, and this is our new word today. All right, so this is one of our first theorems. This is on page 351. Important piece of information here about a tangent. The first thing that we know about a tangent is that if a line is a tangent, and I have it in pink here. Oops. Oh, redo that. Here we go. If it intersects only at one point, it's a tangent, right? We talked about that. This point here, I guess I should have gone back over here and told you if you want to put this into your notes and add that. Let's do it in black. This is called the point of tangency. Right there, it's one intersection. It's called the point of tangency, and it's where it is tangent to the circle. Okay, just making sure I'm spelling that right. Okay. If you have a tangent line, it has a point of tangency right there. And uniquely, if any line only intersects at one point on that circle, then it is, you guessed it, perpendicular to some radius. Now again, we could have all the radius in the world. You could go all the way around, and there are so many that you could have on any given circle. But any line of tangency, any tangent line to a circle, has a radius that would go through this same point of tangency and to its center point. And the relationship between this radius and this tangent line is that they are perpendicular to each other, or creating 90 degrees. Neat, huh? All right, so as normal, a lot of our theorems just kind of one says one thing and the other says the exact same thing the opposite direction. So what we can then say is if I have a line in a plane of a circle, so if it's just in the same given plane, if a line in the plane of a circle is perpendicular to a radius, okay, so I'm given right here that it's perpendicular. Okay, and I know that this is just some line. Right now, all I know is it's a line. I haven't labeled it to be a tangent or anything. And if it is perpendicular to this is a radius, I can tell that by definition here of it having two endpoints, one being the center and one being the end. Then I can say that this is not just a line, this is a tangent line. Okay, so if you know and if you recognize, hey, perpendicular, I've got some line and it's in the same plane as a circle, and hey, it's perpendicular to this radius, well, it is therefore tangent to the circle. Just like before, I said, hey, I have a tangent line and therefore it made a 90-degree angle. Okay, so if you have a tangent line, you got a 90-degree angle. If you've got a 90-degree angle, then you got a tangent line. Again, in relationship to a radius. That part's really important. Okay, one more. All right, what if we have some circle P? I'm going to show you what it looks like when we write it. And we've got some point X way out here. Okay, he's in the same plane, but he's not touching the circle. He's not nearby, any of those things. A unique property about tangent lines, or segments in this case, we're going to talk about why they're segments, is that if I were to draw a line through point X that is also tangent to my circle, let's see if I can do this here, and another one this direction. Okay, all right, here's point X, and these are tangent, meaning they only intersect my circle at one point. Well, if I mean, this is true for the line, but it's also, we're going to call it a segment. If I stop this pink line right here, and I stop it here, I'm just going to make it a segment, okay? So I guess I'll put that back on there. If I make this a segment from my circle here, a tangent point on the circle, to this point out here, called X. And if I come from this point X and I create a line segment to another tangent point on my circle, well, there's a unique property now. I know that this line segment has to be congruent to the other. So let's call this A, and let's call this here B, just so that we can write this out a little bit. My line segment AX is going to be congruent to BX. Okay, why? Well, the theorem states that if you have a tangent line, again, it has to be tangent, so I suppose we should put this radius in here and show this to be a 90-degree angle, and show a radius here to be a 90-degree angle. You do not have to have those. It could say in your given information that it's tangent. It doesn't have to show that it's perpendicular to the radius, but that is a good way to just be sure also. Okay, so if you have two line segments that go through the same point and they're both tangent to the same circle, then we know that those lines are congruent. And then we could say that they're equal, and then we could go through a ton of other things because of that information. So I think that one's a little bit confusing, so I'm just going to draw another circle, and we're just going to real briefly kind of talk through this, and I'll show you a couple different points here. Okay, so if I had a line segment that was tangent to this circle and tangent to the same circle going through this same point, I'm going to call it A this time, I now know that this line segment is congruent to that line segment. Okay, so let's do another color to call it something different. If I had another point, it could be somewhere else. And forgive my lack of ability to draw here so well on this. Okay, so if I had two other line segments that were tangent to one circle and they go through some exterior point, I now know that that one is also congruent to the other, and so therefore they're equal to each other, and those have the same length. Okay, alrighty. Let's do two more definitions, and then we're going to call it quits on notes. Okay, hang in there. You guys are doing a great job. We're not going to practice any of these. We will next week. We'll go through a ton of other things in practice, but I wanted you to get notes in. We will run one or two things so you feel ready for your online assessment for tomorrow. All right, our definition of our new word is called a common tangent. All right, a common tangent is a line that's tangent to two coplanar circles. Coplanar meaning they're in the same plane. They can't be one on the top of a die and the one on the lower opposite side of a die, or a cube or any type of three-dimensional figure. As long as they're on the same plane, it is just a line that's tangent to both circles, okay? So a line, tangent to two circles. Okay, so let's draw. I know that looks terrible. Hopefully you can hear what I said and write it down. Okay, so it could look like this. Imagine that actually intersected. Okay, remember geometry with me. It requires some imagination. I can't draw it perfectly. Okay, there is a common tangent right there. It's a line, goes on forever in both directions, and it is tangent to circle A and tangent to circle B. Another one could be down here on the bottom. Totally missed the boat on that one. And I can't have it a secant line. It has to just intersect once. This would be easier with a ruler. Okay. Intersects here once and once. Let's pretend those are tangent. If it is tangent to circle A and tangent to circle B, this is what? Yes, a common tangent. There are yet a few more. You could have a line, and I'm using a different color just to keep it pretty. All right, if this is tangent and this is tangent, and again, this would actually have to intersect at one point, but I did not draw my line perfectly. If this line here is tangent to circle A and tangent to circle B, meaning there's one point of intersection, that is also a common tangent. And so lastly, you could also have one that looked like this, and one point of intersection here, one point of intersection here. That is another common tangent. Common tangent is a line tangent to two circles. All right, last one. We're going to talk about having tangent circles. So it's possible to have a circle and another circle, and they share a tangent line. So there is only one point of intersection here. All right. Let's just label this real quickly as circle A and circle B, and this is a tangent line. All right, I need to work on a new stylus, I think. Okay, and we are going to just label this as tangent circles. Oops. Again, just get this information in. We'll cover it more next week. Tangent circles to circles who have one point of intersection or share a tangent line. They are just tangent to the same line at the same point. Okay, not tangent elsewhere. It's not like this down here. This would be a common tangent line. It has to be the same point. Okay, that's the unique property there. All right, let's just run real quickly through some of the things that will be on your quiz assessment tomorrow. I'm not always going to do a review in your videos, but y'all, I know it's hard right now, and there's so much going on and so much confusion. So I'm going to cover mostly what I've heard is struggling a little bit with a sector. So we're going to look at that. Mostly need to be able to identify the different parts of a circle. We talked about that already at the beginning, so go back to the beginning of this video, review, be able to identify the different parts of a circle. It might be a chord, it might be a diameter, a radius, a secant, any of those things, and need to be able to identify those, okay? All right, so if we had a circle that looked like this, and I had two radii, and there are two chords here, okay? What if I told you that both of these chords happen to be perpendicular to the radius that they intersect? Well, now we have some unique properties. Again, this is true for congruent circles, or if it's the same circle, congruent circle, meaning two circles that are the same size, shape. But if it's the same circle, then of course it's congruent to itself. It's the same size, it's the same shape. Okay, so I'm going to kind of point to some of this here, and then we're going to label these. I guess we could just label it now with a few letters, which will help us identify the different parts of this circle. Okay, and those are the points of intersection, respectively. Okay, some of them, again, if it's a chord, the two endpoints are on the end of the circle there, and it does not go through the center. If it does, that's a diameter, and that's still technically a chord. Every diameter is a chord, but it's a unique one. Okay, all right. So if I know that these are perpendicular, then there's a lot of information that I also know. If I know that IG is equal to EB, then I can say, well, let me back up again. I think I'm kind of doing two things at once. Okay. If I know that this is where's my pointer here? If I know that this is a right angle, then I know that this is bisected. Let's cover that first. Okay. Now, secondly, if I know this here at angle F is a right angle, then I know that GI is bisected. That means that I know that GF is congruent to IF. If EB intersects AC at a right angle, I know that ED is congruent to DB, this section right in here. Okay? Now, if I have more information, let's say I knew that GI was equal or congruent to EB. So let's point this out. This yellow line, if both my chords are equal to each other, well, they're still bisected because I still know it's a 90-degree angle. If I know that these guys are equal to each other, there's a lot of information that I then know. I also know, if these are equal to each other, that this little section in here, let's pick a new color, okay, is also equal to the other one. And let's name it. If GI is congruent to EB, then AD is congruent or equal to AF as well. Okay, that's probably some of the most important information, knowing those relationships. If it's the same circle, it's congruent. If there are two circles and they're congruent, that works as well. Okay, so I could plug some information there, and I also can come up with lots of right angles. So I'm going to try to do that. Let's see sorry, this is a little bit of an obnoxious color, but I'm limited on my color choices here. All right, I try to make it not quite as bright. There's a right triangle. Here's another right triangle. Right, all of these are right angles now. Here's another right triangle and another right triangle and another right triangle. Anytime you have a chord and it creates a 90-degree angle, or it's perpendicular to a radius, you now have all of these little right triangles. And the beauty of the right triangle is the Pythagorean theorem: a squared plus b squared equals c squared. Don't forget, in your interactive notebook, we also algebraically put our information in how to find a, b, or c on their own. Okay, if you understand those things and you understand the different parts of a circle, being able to identify a chord, diameter, radius, and secant, you should be good. Don't worry, you can use your interactive notebook in your book on this. You guys should be doing a great job. The last thing I wanted to cover was just backing up a little bit. I told you guys we would look at covering a sector of a circle. Okay, and that's just finding the area of a piece of a circle. Okay. All right, so here's a circle. How many degrees go all the way around a circle? 360 degrees. Good. So if I know there's 360 degrees all the way around, I know I could really separate this into, and this is where pie graphs come in handy. Anytime you have some circle, you might separate it and say, hey, this is my section of classmates that like science the best. This is a section of classmates that like Bible the best. This is the class of section of classmates that like math the best. And I suppose I should have made this the largest if I'm going to say, but maybe we'll say this is who likes lunch the best, right? You can separate them, and it's by, these are essentially sectors, right? You've made a different pie of your circle. And then what made it so complicated was that we had to call it some theta in here, and that was simply just the angle measurement that associates with it or goes with it. Okay, technically you could divide this into 360 tiny little pieces, and each one of those is 1 degree. Okay, 1 theta. Now it's not 1%. You'd have to divide that into 100, and that's quite a process. We were going to do a whole project on that, but we won't without doing it all together. So someday maybe. Okay, so I'm just going to kind of scooch over and start a new circle here. So if I have a circle, and let's say I have this pink sector, okay, and it's a section of my circle, and I want to know, hey, how much is that area of that sector? Well, I know that the area of the entire circle is pi r squared, right? The whole circle is 3.14 times whatever my radius is, and then, well, square the radius, then multiply by 3.14, and I found my area, some measurement, and it's going to be units squared, okay, based on whatever your radius is. Well, if I know I only have a section of this, I need to know how much of that section, how many of those 360 degrees all the way around are inside of this one circle. Well, that's why we use divide by 360, because we know that there's 360 degrees all the way around. So if this is some angle measurement, it's out of the 360. Okay, so that's where our formula comes from. It's out of my theta, or however many degrees. If I said that this was 60 degrees, I would use 60 degrees here. Okay, let's go back to here. Divided by 360 is out of 360. This section is my sector. Okay, and in order to find the area, I still have to multiply by pi r squared. Forgot the pi there. Some section of, or multiply by, the area of the whole circle. It's some fraction of the whole circle. That's really what we're doing. Just a fraction of my entire circle is 60 in this case, 6360ths of my entire circle. And the entire circle's area is this, okay? And so I can't really tell you what this area is without coming up with some sort of a radius, but hopefully that helps you a little bit to kind of talk through it that way. All right, well, miss you guys. Hope you're doing well. Reach out, send me a text of something you do over Easter, or Instagram a picture of your indoor egg hunt without all of your friends or something like that. But we'll catch you guys later. Have a great day.